Hi. Last time I started with the promise that I would deduce an Euler product description. That will be achieved in this video. Okay, that's our case-by-case computation of this quantity. So recall that we were interested in this kind of expression. By the previous result, this can be bounded as first we write the first case of the computation, which gives 1, and next come terms of the second cases, which gives, so first the choice of I0, the choice of the prime ideal over P, and case 3 is finitely many 1 over P squared. And of course, if P divides W, there are much fewer terms, namely these terms and these terms are not here. But since I am talking about inequalities, let's write this way. Now we know that this norm is at least P anyway, so we can bound this value by from above by so the largest term among these is bounded by P to the power of minus 1 minus. This is the largest term, and there are bounded number of them. So let's write like this. And I can do an operation like this. 1 minus P to the power of minus bounded quantity. So this is because, so for epsilon and positive number, we know that 1 minus epsilon to the power of minus c is by Newton's binomial law. So this is the first term, and the second term is, so this is the binomial coefficient in the power of minus epsilon. This term is positive, and the third term looks like so this is the product of 6 negative numbers. So this is again positive and positive terms. So therefore this is larger than 1 plus c epsilon. So it follows that, I'm using this as this is bounded from above by this thing. So this thing is bounded above from this thing. Yeah, a little tricky piece of computation. And now I recall that the zeta function has the following Euler product description. So the previous expression is zeta function 1 plus to the power of 1. In particular, this converges. So I mean this the Euler product describing the zeta function is known to converge absolutely if the real part of S is larger than 1. Yeah, so this shows the convergence of this sum. Which was our intermediate goal. So what does this convergence tell you? So recall that we were considering the following expression. So I slightly rewrite the integration part. I write this as an integral over 2m-dimensional domain, and I prepare the copies of the variable psi indexed by I and k. And the average of the indicator function. So this is the quantity that our theorem computes. Yeah, so the convergence allows us to exchange this sum and integration. So equals so we integrate and so here is a quantity that doesn't depend on the choice of ideals. Should have written here. And next come sum Möbius and non and we have the expectation part. And we integrate this whole thing. Now we want to consider this sum part. So before taking a sum for any fixed tuples of ideals, fixed tuple of ideals and variables psi, we will rewrite this quantity first. yeah, I mean, we know that this thing is multiplicative with respect to the decomposition into p parts, so product over prime numbers. So I put the p part everywhere. The exponent is the same. I forgot I. So this expectation part is also, so this is the version depending on the p part. But we know that what this part looks like. I mean, I'm repeating part of our preceding discussion, so there might have been a more economical way of doing things. In any case, we know what this our factor looks like. The first case was, sorry, from this moment on, I am actually taking the sum over all the possible choices of ideals, is when all these ideals are the unit ideal, which gives 1. And the second case was when these are the unit ideals except for one single index I. So this gives the special index, and yeah, I mean, almost all are the unit ideal, and the remaining few are a prime ideal. So that was case 2, so that's why I'm doing it. And then there were 2 subcases. One was when this and this are both p, then this gives what? So the Möbius part gives 1 minus 1 times minus 1, which is plus 1. And this norm, so I have plus norm of the prime p, and the power exponent becomes the sum of the the relevant 2 of them. So 2 plus I psi I1 plus psi I2. So the other subcases were, this is prime, but the other is the unit ideal. In this case, the Möbius function becomes minus 1. So minus norm, only one non-trivial contribution. And the opposite case. So the other variable. So this is the case 2. Then case 3 gives a bounded number of something which is at most 1 over p squared. No, I mean, and I have contribution from this factor, And yeah, this will be, I forgot to include it in the second case, so inverse of these guys. And I will use the fact that 1 plus a small number times 1 plus another small number is almost equal to 1 plus the small number, both of them. Yeah, I use this backwards, so I can write this kind of sum into a product. So this is almost equal to and yeah, let me see. So yeah, note that also that. So if P divides W, large W, or equivalently, this is at most small w, then the expectation part was 0. If at least one ideal is a proper ideal. So then this eliminates all these cases, terms. Yeah, so we are taking the product for primes larger than small w. And next I write a factor coming from this. And the contribution from 1 over p squared is much smaller, so we can ignore it. And now I also use the fact that 1 plus epsilon is almost equal to 1 minus epsilon inverse to rewrite the first term here as, so this becomes minus and this becomes inverse. And then these factors look like the zeta function. The zeta function of your number field at 1 plus 2 plus so here I have the inverse, and this is not quite true yet because we are taking the partial product, so we have to remove what we have excessively multiplied. 1 minus something. And yeah, here in the denominator we are dealing with a finite product, so it turns out that each factor can be approximated by, because R is very large, it can be approximated by 1 minus norm inverse. Note that we are using the fact that the domain of integration has been restricted to an interval of size square root of log R. And then we know that this product is the tangent function. Yeah, let's recall that this large W was the product of smaller prime numbers. Yeah, so basically this denominator explains the totient function factor in the statement of our theorem. Yeah, next time we will continue the estimate of this part using the pole of the zeta function, and then we will do the integration.